For millennia, humanity gazed at the night sky, a canvas of stars, wondering about its endless expanse. We've come to understand our home, the Milky Way, as a vast island of stars. But what truly lies beyond its familiar spiral arms? What is past the very edge of our galactic home, and how far does the cosmic tapestry truly unfurl? This journey seeks to explore the profound answer. The edge of a galaxy isn't a sharp boundary like a planetary atmosphere. Instead, it's a gradual decrease in stellar density, the point where the concentrated galactic disk begins to thin out into a diffuse halo. This halo is populated by ancient stars and globular clusters, gravitational remnants of the galaxy's turbulent formation, slowly dissolving into the cosmic void. Our Milky Way spans an astonishing 100,000 light-years across, home to hundreds of billions of stars. Yet, even this immense structure is just a tiny speck in the grand scheme of the cosmos. We reside about two-thirds of the way out from the galactic center, within a stable region, orbiting the supermassive black hole at Sagittarius A. Beyond the visible disk, the Milky Way extends into a massive, nearly spherical halo of dark matter. This invisible, mysterious substance accounts for roughly 85% of the galaxy's mass, providing the gravitational scaffolding that holds everything together. Without it, our galaxy, and indeed all galaxies, would simply tear themselves apart through rotational forces. The true outer boundary of the Milky Way is thus defined by the edge of this dark matter halo, extending perhaps as far as 200,000 to 300,000 light-years from the galactic core. At these extreme distances, the gravitational influence of our galaxy becomes negligibly weak, giving way to the vast intergalactic medium. This intergalactic space is not entirely empty. It's permeated by a superheated plasma of hydrogen and helium, the remnants of the early universe, incredibly diffuse yet ubiquitous. This tenuous medium, though almost a perfect vacuum, contains more matter than all the stars in the Milky Way, acting as the universe's pervasive cosmic breath. Immediately beyond the Milky Way's halo lies our cosmic neighborhood, the local group. This gravitationally bound assembly of over 80 galaxies is dominated by two massive spiral galaxies, our own Milky Way and its spectacular counterpart, Andromeda. They are colossal cosmic islands, gradually pulling themselves closer. Andromeda, also known as M31, is even larger than our Milky Way, boasting an estimated 1 trillion stars. It dominates the sky in the Andromeda constellation, visible to the naked eye as a faint, fuzzy patch. Its sheer size and proximity make it the most prominent example of what lies just beyond our galactic confines. In about 4.5 billion years, our two colossal galaxies, Milky Way and Andromeda, are destined to collide. This is not a destructive smash, but a graceful, slow merger, where stars rarely hit each other due to the immense distances between them. New gravitational interactions will reshape the entire local group into a new elliptical galaxy, Milkomeda. The local group also contains numerous smaller dwarf galaxies, like the Magellanic Clouds, orbiting the larger spirals. These are often irregular or elliptical in shape, containing only a few billion stars. They are the cosmic debris, remnants of gravitational interactions, some being slowly absorbed by their larger neighbors. Venturing further, our local group is merely a peripheral member of the much grander Virgo Supercluster. This immense structure spans over 110 million light-years and contains thousands of galaxies, grouped into hundreds of smaller clusters and galaxy groups, all gravitationally attracted toward its dense center, the Virgo cluster. The Virgo Supercluster itself is only one lobe of an even more colossal structure dubbed the Laniakea Supercluster, Hawaiian for immense heaven. Discovered in 2014, Laniakea encompasses over 100,000 galaxies spread across 500 million light-years, all flowing towards a common gravitational basin, defining our true cosmic address. Within Laniakea lies the enigmatic Great Attractor, a region of immense gravitational anomaly that pulls the Milky Way and all galaxies in our part of the universe towards it. Its exact nature remains elusive due to obscuration by our galaxy's disk, but it represents a powerful force shaping the dynamics of our vast cosmic region. Beyond these superclusters, we encounter the very fabric of the cosmos, the cosmic web. This is the largest known structure in the universe, a vast, interconnected network of galaxy filaments and clusters, separated by immense, nearly empty voids. It's the skeleton upon which the universe is built, a testament to gravity's power. These cosmic filaments, often described as threads, are massive, elongated structures where galaxies cluster together. They are the densest parts of the cosmic web, acting as galactic highways, funneling matter from the voids into the richer clusters and superclusters. These threads can span hundreds of millions of light-years. Conversely, the voids are vast, largely empty regions within the cosmic web, largely devoid of galaxies, gas, or dust. They represent the emptiest places in the universe, spanning hundreds of millions of light-years. While not entirely empty, the density of matter within them is incredibly low. Some configurations of these filaments and voids form even larger structures known as walls, like the Sloan Great Wall or the Hercules Corona Borealis Great Wall. These are colossal sheets of galaxies, stretching for billions of light-years, representing the largest single structures observed in the universe. As we zoom out further, we start to confront the limits of our observation. Due to the finite speed of light and the universe's expansion, there's a boundary to what we can see, the observable universe. This cosmic horizon isn't a physical edge, but a limit to how far light has had time to travel to us since the Big Bang. The cosmic horizon defines a sphere roughly 46.5 billion light-years in radius, centered on Earth. This distance is far greater than the universe's age multiplied by the speed of light, due to the continuous expansion of space itself. Objects that emitted light billions of years ago are now much farther away. This means we can only see light from regions close enough for light to have reached us within the universe's 13.8 billion-year history. Anything beyond this sphere, while physically existing, remains forever hidden from our direct observation, a truly boundless and enigmatic unknown. The universe's expansion isn't uniform. Fueled by dark energy, this acceleration means that even light from some distant galaxies that we can currently see might eventually recede beyond our observable horizon, forever disappearing from our view. The cosmos is actively pulling itself apart. So what truly lies beyond the observable universe? We cannot know with certainty, but theoretical models propose several fascinating possibilities. The most straightforward is that space simply continues, filled with more galaxies, clusters, and cosmic web structures, endlessly stretching into infinity. If the universe is spatially infinite, then any pattern or structure, given enough space, must eventually repeat. This mind-boggling concept suggests that somewhere, billions of light-years away, there could be exact copies of ourselves or alternate versions of Earth, existing in parallel but causally disconnected realms. Another possibility is that our universe, vast as it is merely one bubble or pocket universe within a much larger, encompassing multiverse. This concept arises from inflationary cosmology, where an early, rapid expansion of space could have spawned countless such bubbles. In this bubble multiverse, each universe could have different physical laws, fundamental constants, and initial conditions. Some might be hospitable to life, while others might be barren, collapsing, or expanding too rapidly, an endless permutation of cosmic possibilities. Some theories suggest our universe might be just one membrane, or brane, floating in a higher dimensional space called the bulk. Other branes, representing other universes, could exist parallel to ours, perhaps occasionally interacting through gravitational ripples leading to cosmic events. Quantum mechanics offers another interpretation of the multiverse, the many worlds interpretation. Every time a quantum measurement is made or a choice is taken, the universe is hypothesized to split into multiple parallel realities, each representing a different outcome. While these concepts are highly theoretical and currently beyond empirical proof, they highlight the profound implications of what lies beyond our current cosmic reach. They challenge our very understanding of uniqueness and the ultimate scale of reality itself. Let's consider the fundamental components that shape the universe even beyond the galactic edge. Dark matter, as mentioned, is an enigmatic substance that doesn't interact with light, making it invisible. But its gravitational influence is profound, acting as the glue for galaxies and larger-scale structures. Astronomers infer dark matter's existence from galactic rotation curves, the gravitational lensing of distant objects, and the patterns in the cosmic microwave background. Without it, our current cosmological models simply don't make sense. Galaxies would spin apart, and structure wouldn't form as observed. Even more mysterious is dark energy, the invisible force accelerating the universe's expansion. Discovered in 1998, its existence overturned previous assumptions that gravity would slow the expansion. Dark energy makes up roughly 68% of the universe's total energy density. Dark energy's nature is one of cosmology's greatest puzzles. Is it a cosmological constant, an inherent property of space itself, or a dynamic field like quintessence evolving over time? Its behavior will ultimately determine the universe's far future. The very early universe gives us clues about what might lie beyond. The cosmic microwave background, or CMB, is the oldest light in the universe, a faint echo of the Big Bang. It's a snapshot of the universe when it was only about 380,000 years old, highly uniform, yet with tiny temperature fluctuations. These minuscule temperature variations in the CMB are the seeds from which all structures in the universe grew. Denser regions eventually collapsed under gravity to form the first stars, then galaxies, and eventually the vast cosmic web we observe today. Inflationary cosmology proposes that immediately after the Big Bang, the universe underwent an incredibly rapid, exponential expansion. This brief period smoothed out initial irregularities and stretched quantum fluctuations into the larger-scale structures seen in the CMB. This inflationary epoch is critical for understanding the uniformity and flatness of our observable universe. Without it, the Big Bang model struggles to explain these observed properties, making inflation a cornerstone of modern cosmology. Beyond the observable, the universe's flatness, suggesting infinite spatial extent, might also be a consequence of inflation. The tiny portion of the universe we can see effectively appears flat, like standing on a giant sphere due to its immense curvature. The universe's ultimate fate also depends on what lies beyond our current reach and the nature of dark energy. Will it continue expanding indefinitely, or will gravity eventually win, causing it to collapse back in a big crunch? If dark energy's influence strengthens, the universe might face a big rip. All structures, from galaxy clusters to individual atoms, would eventually be torn apart as spacetime expands infinitely fast, leaving nothing but isolated particles. Alternatively, if dark energy weakens or behaves differently, the universe could eventually begin to contract, leading to a big crunch, a reversal of the Big Bang, where all matter collapses back into an incredibly hot, dense state. The most widely accepted scenario, given current measurements of dark energy, is the heat death or big freeze. The universe continues to expand, cool down, and grow increasingly empty as stars die, black holes evaporate, and all energy dissipates into a uniform, cold void. These ultimate fates underscore the transient nature of even the grandest cosmic structures beyond our galactic edge. The processes that govern them play out on unimaginable timescales, reminding us of the universe's dynamic and evolving character. Beyond the visible and theoretical edges lies the profound philosophical question: is there a purpose to this immense cosmic sprawl, or is it simply a grand, indifferent mechanism driven by fundamental forces, with life as an accidental, ephemeral flicker? The scale of what lies beyond is humbling. Our galaxy, our supercluster, even our observable universe are like tiny islands in an ocean of unimaginable vastness. This perspective alters our perception of our place, from being central to being infinitesimally small. Yet despite our smallness, our capacity to unravel these cosmic mysteries is immense. Through instruments like the Hubble and James Webb telescopes, we continuously push the boundaries of what's observable, peering deeper into cosmic time and greater distances. Every new observation refines our understanding, sometimes overturning long-held beliefs, constantly reminding us how much more there is to learn. The universe is a grand classroom, and we are perpetual students, forever seeking answers to its deepest secrets. What lies beyond the galactic edge, therefore, isn't just a spatial question. It's a journey through cosmic scales, across epochs of time, into the realms of theoretical physics, and ultimately into the very nature of existence. The true edge of the universe might be forever beyond our grasp, but the pursuit of that edge, the quest for knowledge, is what defines our evolving understanding of everything. It's a testament to the insatiable human curiosity that propels us to continually explore. Consider the sheer volume represented by the observable universe. It contains an estimated 2 trillion galaxies, each home to billions of stars. This incredible density of cosmic structures is a testament to the universe's immense production scale. Each of these galaxies, from giant spirals to faint irregulars, evolved over cosmic time, driven by gravity, gas dynamics, and feedback from supermassive black holes. Their diversity reflects billions of years of cosmic history playing out simultaneously. When we look beyond our galactic edge, we are also looking back in time. Light from distant galaxies takes billions of years to reach us, offering glimpses of the universe as it was in its infancy, revealing clues about early galaxy formation and evolution. The most distant objects we've observed are quasars, incredibly luminous active galactic nuclei, powered by supermassive black holes accreting matter. These cosmic beacons allow us to probe the universe when it was less than 1 billion years old. The formation of these early structures challenges our models. How did such massive black holes and galaxies form so quickly after the Big Bang? This remains an active area of research, pushing the limits of our understanding of cosmic assembly. The distribution of galaxies across the cosmic web isn't random. It reflects the initial quantum fluctuations from the inflationary epoch. These tiny ripples in spacetime became the gravitational seeds for everything we see today. The universe's larger-scale homogeneity and isotropy, meaning it looks roughly the same in all directions and at all places on large scales, is a fundamental assumption for our cosmological models. This cosmological principle is supported by CMB observations. However, recent discoveries of enormous structures like the Hercules Corona Borealis Great Wall challenge our understanding of this homogeneity. These colossal formations push the limits of what a random distribution should allow, prompting new theoretical considerations. The universe beyond the galactic edge is also a laboratory for extreme physics. Supermassive black holes, neutron stars, pulsars, and hypernova all reside within these distant realms, showcasing phenomena beyond anything reproducible on Earth. Gamma-ray bursts, the most powerful explosions in the universe, originate from the collapse of massive stars or the merger of neutron stars, often in very distant galaxies. These brief, intense flashes illuminate even the most remote corners of the cosmos. Gravitational waves, ripples in spacetime, detected by observatories like LIGO and Virgo, offer a new window into these extreme events far beyond our galaxy. They reveal the cosmic dance of black holes and neutron stars, unheard of until recently. These cosmic messengers aren't light. They are distortions of space itself, carrying information about cataclysmic events across astronomical distances, unhindered by dust or gas. They open avenues for multi-messenger astronomy, combining forces to understand the universe. The composition of matter throughout the universe beyond our galaxy is remarkably similar. About 75% hydrogen and 25% helium, with only trace amounts of heavier elements, all forged in the hearts of stars and in supernova explosions. The cosmic origins of these elements are fundamental. Hydrogen and helium were created in the first minutes after the Big Bang, while virtually all other elements, including those essential for life, were subsequently synthesized within stars. Thus, the atoms that make up our bodies, our planet, and our galaxy were once forged in distant, ancient stars that died long ago, scattered across the vastness of space, eventually coalescing to form new cosmic structures. We are literally stardust. The universe's expansion doesn't stretch objects held together by fundamental forces like atoms or even galaxies. It's the space between gravitationally unbound objects that stretches, leading to separation on cosmological scales. This subtle distinction is crucial for understanding why we are not torn apart by the expansion. Yet galaxies are rapidly receding from one another further reaches. Local gravity triumphs over the expansion of space on smaller scales. The ultimate fate of information in the universe is another profound question that relates to what lies beyond. If the universe expands into heat death, does information truly disappear, or is it preserved in some fundamental way? Many scientists believe information is conserved, even after black hole evaporation, implying a deep, underlying order to the cosmos that persists even in the most extreme scenarios, hinting at a hidden reality beyond our current grasp. The concept of nothing in cosmology is also fascinating. What existed before the Big Bang? If spacetime emerged from the Big Bang, then before might not exist in the conventional sense, pushing the boundaries of philosophical thought. Some theories suggest a cyclic universe, where a big crunch leads to another Big Bang, creating an endless cycle of expansion and contraction. This would imply an eternal universe with no true beginning or end, constantly regenerating itself. Such models offer a different perspective on what lies beyond, not a spatial edge, but a temporal one, beyond which the current iteration of our universe may not have existed, or from which it emerged from a previous cycle. The anthropic principle questions why the fundamental constants of the universe are so finely tuned to allow for life. Could this imply that our universe is one of many, and we simply find ourselves in the one where life is possible? This philosophical concept ties into the multiverse idea, where a vast ensemble of universes with varying constants allows for the statistical likelihood of at least one emerging with properties conducive to stars, galaxies, and intelligent life. The exploration of beyond the galactic edge is therefore not solely the domain of astronomers, but also cosmologists, particle physicists, and philosophers, pushing the boundaries of human thought across multiple disciplines. Our understanding of the universe has been a journey from geocentric to heliocentric, then to galactocentric, and now to an awareness of a vast, expanding cosmic web with our galaxy as a mere knot within it. Each step in this cosmic revelation has challenged our preconceived notions and expanded our horizons, proving that the universe is far more complex and majestic than we could have ever imagined. The search for extraterrestrial intelligence, SETI, also has implications for what lies beyond. If life is common, then other intelligent civilizations could exist in countless galaxies beyond our own, vastly expanding humanity's cosmic neighborhood. The Drake equation attempts to estimate the number of detectable civilizations by considering various astrophysical and biological factors. While highly speculative, it frames the immense possibilities if life is not unique to Earth. The Fermi paradox, however, asks, if intelligent life is common, where is everybody? The vastness of space and time suggests that even if civilizations exist, the distances involved make communication and detection incredibly challenging. Perhaps advanced civilizations are so far beyond our galactic edge that their signals simply haven't reached us, or they operate in ways we cannot yet comprehend, adding another layer to the enigma of the cosmic beyond. The future of astronomy promises even more astonishing discoveries. Next-generation telescopes, both ground-based and in space, will push the boundaries of observation even further, peering into the cosmic dawn and beyond. Gravitational wave detectors are becoming more sensitive, potentially allowing us to observe the mergers of distant supermassive black holes from the very early universe, providing insights into the seeds of galactic formation. The development of quantum technologies and advanced computational models will further refine our simulations of the early universe and larger-scale structure formation, helping to bridge the gap between theory and observation. These advancements mean that what lies beyond the galactic edge isn't a static question, but an ever-evolving frontier of scientific inquiry, continually revealing new layers of cosmic complexity to our understanding. The very concept of nothingness, or the vacuum of space, takes on incredible significance beyond our galaxy. It's not truly empty, but filled with virtual particles constantly popping in and out of existence, a quantum foam. This vacuum energy could potentially be related to dark energy, suggesting that the expansion of the universe is driven by the inherent energy of empty space itself. This would be a profound unification of quantum and cosmic scales. The shape of the universe on its grandest scales is also tied to what lies beyond our current observations. Is it truly infinite, flat, or does it eventually curve back on itself, like a giant cosmic sphere or saddle? Current data from the cosmic microwave background strongly suggests our universe is remarkably flat. This implies an infinite expanse where parallel lines never meet and the universe does not curve back on itself. However, measurements always have uncertainties. A very slight curvature, too small to detect with current instruments, could still mean the universe is finite but unbounded, like the surface of a sphere, just on an incredibly colossal scale. The universe beyond the galactic edge is also home to primordial black holes, theorized to have formed in the early universe, possibly contributing to dark matter. Their existence would profoundly impact our understanding of cosmic evolution. These tiny, ancient black holes, if they exist, would be incredibly difficult to detect, but their gravitational imprints on dark matter halos or distant light could one day reveal their elusive presence. The very first stars, known as population III stars, were massive, short-lived, and composed solely of hydrogen and helium. They forged the first heavy elements, paving the way for all subsequent star generations billions of light-years away. These stellar behemoths lived and died in the cosmic wilderness beyond our early galaxy's influence, their explosive ends seeding the intergalactic medium with the raw materials needed for complex chemistry and, eventually, life. The largest structures in the universe, the superclusters and walls, aren't gravitationally bound. They are still expanding along with the universe, whereas galaxy clusters within them are bound and will remain so. This means the cosmic web, while seemingly stable, is actually slowly disintegrating on its largest scales due to dark energy, with filaments gradually thinning and voids becoming even emptier over eons. The universe's mass distribution gives us insights into its origins. The observable universe, for example, appears to be remarkably flat, a key prediction of the inflationary theory. The mystery of baryogenesis, why there's more matter than antimatter in the universe, is fundamental to understanding our existence. If there were equal amounts, all matter would have annihilated, leaving only light. This asymmetry, while slight, allowed for the survival of protons, neutrons, and electrons, the building blocks of everything we see beyond the galactic edge and within it, from stars to life itself. The search for fundamental particles beyond the standard model of particle physics often involves cosmic observations. Dark matter particles, for instance, are proposed to interact weakly, requiring sensitive cosmic detectors. Cosmic rays, high-energy particles from distant galaxies, bombard Earth constantly, providing a unique window into extreme astrophysical processes far beyond our solar system. The oldest stars in our galaxy's halo are vital for probing the universe's history. These ancient population II stars have very low metallicity, holding clues about the chemical composition of the early universe. These stars hint at an even earlier era, predating the formation of our galaxy, providing observational anchors for theories about the initial star formation and the very early phases of cosmic evolution. The universe's accelerating expansion, driven by dark energy, means that eventually all galaxies beyond our local group will recede beyond our observable horizon, making them forever invisible to future astronomers. The vast cosmic distances and the light travel time mean that much of what lies beyond is already history. We are effectively staring into the universe's past, observing events that unfolded billions of years ago. The future observable universe will shrink due to this acceleration, leaving us effectively alone with our tightly bound local group as an island in an increasingly empty cosmic ocean. This cosmic isolation provides a profound perspective on our place in the universe. Our immediate galactic neighborhood will be the only visible remnant of the vast cosmic web we currently perceive. The universe's topology, its global shape, could also be more complex than simply flat, spherical, or saddle-shaped. It might be finite but multi-connected, like a cosmic donut or a more intricate geometric shape. Such complex topologies would mean that looking far enough in one direction could eventually bring us back to our starting point, albeit from the opposite direction, creating a truly mind-bending cosmic journey. The search for cosmic strings, hypothetical one-dimensional topological defects left over from the early universe, is another pursuit reaching far beyond galactic confines, potentially revealing clues about fundamental physics. These strings, if they exist, would be incredibly massive and could warp spacetime, creating observable gravitational lensing effects or patterns in the cosmic microwave background. Our understanding of beyond the galactic edge is constantly evolving, not just with observations, but with theoretical models. Each new insight reshapes our cosmic map and deepens the questions we pose. The fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces govern all interactions, both within our galaxy and across the vast emptiness beyond it. Their precise balance is crucial. The universe's isotropy means these laws appear to be uniform everywhere, from the smallest quantum interactions to the largest cosmic structures, allowing us to extrapolate our local understanding to the furthest reaches. Yet the search for a unified theory of everything that can describe all forces under a single framework remains the holy grail of physics, promising even deeper insights into the underlying reality of the cosmos. What lies beyond could also be influenced by cosmic inflation's connection to quantum gravity. Some theories suggest inflation might have been driven by quantum effects, becoming dominant on cosmological scales. Quantum vacuum fluctuations, those brief appearances of particle-to-particle pairs, are thought to have been stretched incredibly large by inflation, becoming the seeds for all structures we currently observe. The universe's beginning might not have been a point, but rather a bounce from a previous contraction, a cornerstone of some cyclic universe models. This would mean no singular beginning, but an eternal continuum. Dark flow, an anomalous bulk motion of galaxy clusters that cannot be explained by visible matter, hints at gravitational influences from regions beyond our observable universe, a possible tug from an unseen cosmic structure. This unexplained velocity field, if confirmed, would provide direct evidence of components of the universe that are causally disconnected from us, pushing the boundary of beyond the galactic edge further out into the unknown. The universe beyond our galaxy isn't just a collection of objects. It's a dynamic system constantly undergoing transformation, driven by gravity, dark energy, and the fundamental laws of physics. The incredible precision required for life to emerge also suggests a profound connection between the universe's ultimate structure and our very existence, a delicate balance that hints at deep cosmic harmony. The distribution of elements across the universe beyond the galactic edge is surprisingly uniform, indicating that the initial Big Bang nucleosynthesis and subsequent stellar processes occurred consistently throughout. The vastness also underscores the rarity of encountering other complex life. Even with billions of galaxies, the distances are so immense that contact remains a formidable, perhaps impossible, challenge. The concept of time itself takes on new dimensions when considering what lies beyond. Cosmological time scales are so immense they challenge human comprehension, stretching from femtoseconds after the Big Bang to trillions of years into the future. The universe's eventual reionization, where the first stars and quasars emitted enough energetic light to strip electrons from neutral hydrogen, transformed the early cosmic fog into the transparent universe we see today. This epoch, billions of light-years away and billions of years ago, transformed the very fabric of the cosmos beyond our nascent galaxy, allowing light to travel freely, enabling our current observations. The study of cosmic dust and gas in the intergalactic medium is crucial. Though sparse, it absorbs and scatters light, influencing our observations of distant objects and providing clues about the cosmic evolution of matter. The most colossal black holes, supermassive ones, at the centers of galaxies, grow by accreting gas and merging with other black holes during galactic collisions, playing a crucial role in shaping their host galaxies, even beyond our own. The universe beyond the galactic edge is filled with remnants of past cosmic violence. Supernova remnants, black hole binaries, and rogue stars ejected from their birthplaces by powerful gravitational kicks. The distribution of these remnants provides a forensic trail, allowing astronomers to reconstruct the history of star formation and death in distant galaxies, far beyond what our own galaxy can reveal. The concept of cosmic bubbles of varying densities formed during inflation affects the larger-scale distribution of galaxies, contributing to the formation of voids and filaments in the cosmic web. These statistical fluctuations, amplified by gravity over billions of years, are the ultimate cause of the vast, intricate structures we observe today, connecting the quantum realm to the grandest cosmic scales. Our understanding of galactic evolution is heavily informed by observing countless galaxies at different stages of their lives across the universe, providing a composite history of galactic birth, growth, and death. The universe's chemical enrichment, flowing from dying stars into the intergalactic medium and then back into new galaxies, is a never-ending cycle, constantly building on itself across cosmic time. The presence of water, a fundamental component for life, is detected in distant galaxies and even intergalactic clouds, suggesting the building blocks for habitability are widely distributed across the cosmos. The relentless expansion of the universe means that the light from some of the very first stars and galaxies born in the cosmic dawn might never reach us due to their immense acceleration away from our horizon. This realization puts a temporal limit on our observational capabilities, even if our instruments were perfect. The most fascinating events of the early universe may remain forever shrouded in the expanding cosmic darkness. The search for technosignatures, evidence of technology from other civilizations, extends beyond our galactic edge into the realms of intergalactic signals, hinting at potential communications across vast cosmic distances. The concept of beyond isn't a singular destination, but a multifaceted frontier, spatial, temporal, and theoretical. Each layer peeled back reveals an even grander and more intricate tapestry of cosmic reality. What lies beyond the galactic edge is not just empty void, but a universe brimming with structure, mystery, and profound implications for our place in existence. It's a journey into the immense, the unknown, and the ultimately unknowable. Yet it is this very mystery that compels us, igniting our curiosity to constantly push the boundaries of knowledge, forever striving to glimpse just a little more of what lies beyond the galactic edge.